Our first talk is going to be about McTT, a verified kernel for a proof assistant. So I think we're going to think about the question of should we trust proof assistants, which is a very important question, and Junyoung is going to lead us in the talk. Thank you.
Thank you for the introduction. This work, McTT, is a collaborative work with the Antoine Gaulin, Jason Hu, and Brigitte Pientka. And I'm gonna start with this thing. So nowadays there is the increasing concerns of correctness of software systems. So consort has been a decade thing, and there is the BASFS, which is a verified file system implementation, and there is certiQuest, which is the certified concurrent OS kernels. And there is some other industrial works to verify software systems. Well, popular way of get correctness of software system is using a proof assistant. But a proof assistant is also a specific kind of software system. So how should we, or why do we trust a proof assistant as a software? Common way to work around in this question is that providing a small kernel so that one can check whether that kernel is really correct and reflects the theory. Now the question is that, is it really small? It turns out Rocq has now 41,000 lines of code for its kernel, and suffers from 50,000 bugs since the 2040. And Lin, which has comparably smaller kernel, but written in C++, and has been suffered from the soundness bug as well as stack-port bugs since the 2020. And Agda does not even have kernel. So we need to deal with the entire 100,000 lines of code to trust Agda. And it has been suffered from 80,000 bugs since 2015. So under this situation, why don't you just verify the kernel itself and providing a verified implementation for kernel? Another point of verified implementation is actually, verified implementation is not just about the correctness. We are not talking about verified theory. We want to have an extensible implementation in a sense that one can add more features to the verified implementation. Otherwise, it will be quickly become a meaningless thing. And the streamlined implementation in the sense that verified implementation should not carry any information about proofs. I mean, once verified, the verified implementation should not carry all the noises from proofs to be efficient. And it should be human readable so that readers can check whether the implemented algorithm is correct, not depending on our verification itself, but by reading the extracted code. And maintainer might want to test a feature candidate without fully verifying it because it is after feature candidate, and they might not want to implement after testing it. So here I present the McTT, Mechanized Type Theory, which consists of three parts. First, verified theory. We verify the core Martin-Löf type theory with cumulative universal hierarchy, inductive base type, and other extensions. Second, we verify the algorithm for type checking and normalization of MLTT, and shows that the soundness and completeness with regard to the theory. Finally, we provide the verified implementation, which is extracted from the verified algorithm part of Rocq, and it is streamlined and human readable. All these things is verified in Rocq proof assistant. So let's go into the actual overview of McTT. McTT starts from the stream of tokens, and parser converts it into a concrete syntax tree. And then our operator translates it into abstract syntax tree. And in backend, we evaluate the abstract syntax tree into a semantic domain and read back from there to normalize it. This is a technique called normalization by evaluation. And by depending on this normalization algorithm, we show that we provide the algorithmic components for typing and equivalence, basically conversion checking. And then we prove that this algorithmic component is sound and complete with regard to the syntactic typing and equivalence checking, equivalence judgments. After proving all these properties, we extract the Rocq version into a Kernel version. And then we add some string processors, Lexer and Pretty Printer in OCaml, so that we can get source code and Lexer in OCaml translated into a stream of tokens. And the stream of tokens goes through all the Rocq things and actually into the extracted things, so that we can get the yes or no, basically the answer for the where typeness. So it says yes for the where type terms and no for ear type terms. This entire system is implemented in 20,000 lines of code, and this includes the entire proofs. So excluding proofs, this is around the 10,000 lines of code. Key challenges in this implementation is two. One is encoding of induction recursion in Rocq, and the other is algorithmic type checking with universes. Let's first talk about the encoding of induction recursion. However, before going into encoding of induction recursion, what is induction recursion? Induction recursion is something to do with something like this. So basically, suppose that we have this kind of function, and we want to formalize this within some proof persistent. However, this is not so easy because it's hard to say whether this function terminates or not. So before even proving termination, how can we actually encode this into a proof persistent? One easy way is providing a domain which allows us which plays the role of a termination measure for a function implementation and defines when the function terminates, and function definition that depends on that domain. So basically, when the first case, when the n is greater than 100, then it immediately terminates, so we don't need anything else. And the other case, where the function terminates only when the inner function and the outer function core both terminate, we first say that inner function terminates based on this domain definition, and then says that external function core terminates based on this domain definition. But note that here we use the function we are now currently defining. And in the function definition, we need to pattern match on P to actually define the function, because that's our termination measure. This kind of mutual dependency between inductive type definition and recursive type definition is possible only when we have induction recursion. So induction recursion is a feature that allows to define this kind of mutual definition. But where is induction recursion in our system? It's in normalization by evaluation part. More specifically, it happens when we want to define a semantic equivalent of equivalence rules, which is the evaluation result of equivalence. So this per model part is the problematic part. Why the per model introduces the induction recursion? So per model basically requires two parts. One is the relation or equivalence between types, and the other is a relation between terms. Relation between types is actually defined inductively while using relation between terms. And relation between terms is defined recursively by pattern matching on relation between types. So there is induction recursion because of this relation. Now, question is that now the problem is that Rocq does not support induction recursion. So how can we encode induction recursion in Rocq? A common method is something called Bob-Capretta method, which is named after the Bob and Capretta. But this method does not work for universe hierarchy, full universe hierarchy. So we cannot use this method. And instead of that, we come up with the one key idea that we do not need to compute ER. This ER is used only for proofs, and we never use this ER in terms of algorithms. So we don't need to use ER we don't need to compute ER. Because of that, we can define a proof. We can prove propositions UI as a functional relation that returns ER. Like if we represent it in a judgmental form, it's like this. It says that A and A prime is related in universe I, and that universe I returns the elemental relation ER, which describes the term, the equivalent term in A and A prime. This solves our problem of induction recursion. However, it also gives us one more bonus. Like when we define the UI as a functional relation, should it really be functional relation? By functional, I mean output ER is unique. Should it really be unique? The answer is no. We don't need to be. It doesn't need to be unique because we don't care about what ER is. We only care about what ER relates. It is related to. We don't need to compute ER, and we only care about what ER is actually for. So instead of the functional relation, we can use weakly functional relation. By weakly, I mean output ER is unique up to relational equivalence. By relational equivalence, they relate the same things. Advantage of this thing is that basically we can remove several direct applications of functional extensionality, and basically all applications of propositional extensionality in our proofs. Now, next, go into the next challenge, which is the algorithmic type checking with universes. I put spaces there because by algorithmic type checking, what I mean by is actually algorithmic bidirectional type checking. And let's go into this kind of simple cumulative universe rule. Within this simple cumulative universe rule, we can type check this kind of example. A function that takes y and returns y, and y is in type 0, then the function type pi y in type 0 returns type 1 is where type because we can apply the cumulativity rule on variable y. If we add some more complex structures, like basically one beta radix around the original term, we can still type check as long as it is declarative type check. If we go into the bidirectional type checking setting, in usual bidirectional type checking setting, when we have functional application, function part will be inferred, and this is the inferred type in the inferred type for the function. However, the return type of the function, which we will get after application, does not match the type we want. The problem is that the return type of each function, type 1 and type 0 doesn't match, and there is no way to rip the function between type 0 and type 0 into type 0 and type 1. So we need to avoid simple cumulative universe. Instead, we use a Rocq-like covariance subtyping cumulativity. Basically, we have the subtyping rule and the cumulativity rule and covariant subtyping rule for function type. So if we go back to the same example, the function part still infers the same type, but after application, the type, these two types are now in the subtyping relation. And by applying the subtyping rule, we can get the desired type. This kind of subtyping happens in general for the all negative types. And we added this kind of subtyping rules for negative sigma type as well. There are basically two takeaways from these challenges. One for induction recursion and the other for subtyping. And for induction recursion, the takeaway is that we can encode every induction recursion even when the recursive part, EL, is also in the predictive universe. And the second one about subtyping is that our theory and algorithm should be developed together. So subtyping is added for algorithmic concern, and which was not there for the previous MLTT theory mechanization done by Jason Hu, myself, and Brigitte Pientka. So far, we are talking about the challenges in the McTT, and let's go into the human readable streamlined part. So the upper part is the Rocq definitions, basically just the type part, which describes the implementation for the subtyping checker. And this A and B is a normal form, and it returns either A and B is in subtyping relation or not. And if we extract the entire code into OCaml, what you get is this kind of readable code. By readable, I mean what it does is like clear. When A and B is both the universe, we check its level is in order is less than order, and if both the type A and B are function type, we compare the input type with the equality, and the output type with the subtyping checker. Same happens for the general subtyping. Previously, it was for the normal form, and this one is for general subtyping. And for general subtyping, we return either A and B is in the subtyping relation or not. And extracted code is just like normalizing A, normalizing B, and compare it by normal form implementation. So conclusion is McTT's contribution has contributed to the as the first end-to-end verified kernel with the cumulativity, inductive base type. It has the streamlined type checkers and normalizer of cumulative type universe type theory. Encoding of pure universe hierarchy using predictivity is like different from the Bob Capretta method, and we presented in here as well. And we also presented the design principle based on the interplay of type theory and implementation or algorithm. We basically have two lines of future work. One is for towards alternative or secondary kernel for Coq, Rin, or those kind of existing proof assistant. And for that, we have working on adding this kind of interesting type that can be used for the secondary kernel, propositional equality types, sigma types, and user-dependent inductive types. First two are already finished in our master branch, and the third one is currently ongoing project. And there is another part of the future work. We are envision this as a playground for verified type theories. So we are currently working on a pure type system style type theory implemented on this framework. And we are also envisioning the modal type theory implementation, such as Cocon, based on current system. So far, this was my introduction to McTT, and if you have any question, feel free to ask. Thank you for listening.
Excellent. Let's take some questions.
Oh, thank you. So this kernel was verified in Rocq, right? So in the end, we still have to trust Rocc's kernel to trust this kernel.
Actually, one of the points why I mentioned I put the emphasis on the human readable part, because to distrust this system, you first need to distrust the code, Rocq, and you need to distrust our declarative rules and proofs, and you need to say that destructive part, the problematic part in Rocq, should affect our proofs. And third, after reading the extracted code, you still say that this extracted code does not make sense because it might have some bug here and there. So like there are several layers of trust you need to break. So this one is more like adding a trust layer than like providing a complete unbreakable trust. Yeah.
Hopefully in the future we can bootstrap our trust.
More trust-based.
And we'll keep going,
Yeah.
So I have related questions. The first thing is that there's the logrel project and paper that does very similar stuff.
Sorry?
The logrel project. They have a paper at CVP called Martin-Löf à la coque.
Martin-Löf à la coque, I see.
So I don't know if what's the difference compared to what you're doing, because as a non-expert, it seems very similar to me.
Yeah, in Martin-Löf à la coque, the implementation, there are basically, say, three main differences. The first one is that their implementation is based on something called the reducibility candidate, and our implementation is based on normalization by evaluation. Normalization by evaluation is known to faster for success case and slower for failure case. And as I said, we envision this as a secondary kernel for the proof assistant. So we don't need to care about, we less care about the failure case, because failure case means that the proof assistant, the first kernel has a bug. So we less care about that kind of case. And their system does not have extraction, or like they have extraction, but only the fewer extraction. By fewer, they can take a finite number of steps, and our extraction proves the termination and does not need to depend on the fewer extraction. And third, final one is that our system has a cumulative universe, so we need to use the proof, the impredictive universe for to encode the induction recursion, but their system does not require the induction recursion at all, because their system does not depend on the full universe hierarchy. They just have two universes, basically the types and the terms. Yeah.
So compared to the MetaRock project, I understand the difference is that you prove consistency, but to the cost of not having prop. MetaRock project, you prove consistency, but you don't have prop because of that. Okay.
All right, let's thank our speaker again.